I have updated my 3D simulator so that I can deal with discrete functions. What you see here is the sine function which has been sampled in the frequency domain. We have the frequency axis k omega here. We have the real part of the function here and the imaginary part of the function along this plane here. So I can represent discrete functions in the frequency domain for both the real part and the imaginary part. So let's see what we can do with this. We can adjust the sampling frequency, so you can see the number of samples is being increased. We can also adjust the amplitude. And we can adjust the phase of the signal along the omega axis. And we can adjust the frequency of the signal along the omega axis as well. So that's the frequency being doubled, and that's times 3. And I'll put it back to the value of 1. Now, there's one other thing here that we can do, and that is if we have a function in the time domain, if we shift the function in the time domain, it's equivalent to adding linear phase in the frequency domain. And we can simulate that here now. So if I was to add linear phase, then it's equivalent to allowing each of the little phasors to start rotating. And you can see this rotation starting to occur now. So it means that each of the phasors not only has a real part, but also an imaginary part. And you get this corkscrewing effect. I'll let that run for a little bit further. And you can see it starting to rotate. And what's happening is, as we move up the frequency axis, the phasors further along the frequency axis are rotating quicker than the phasors nearer the origin. So we'll return that back to 0. Now I've shown it only for the sine function, but we can do it really with any function that you can imagine here. So I will add a function in here, and let's say we're wanting to look at the function x squared. Okay, so there's a function there. So in effect, we've taken the function y is equal to x squared. I'll make it a little bit smaller. Okay, so we've taken the function y is equal to x squared in the frequency domain, and we've sampled it. And we can also, again, adjust the signal within the imaginary plane as well, and that's it starting to rotate around the k omega axis. So what we have here is another addition to a powerful little tool that will now allow me to represent signals within the discrete domain. So thank you for listening. I'll get you on the next video. Goodbye.